The air turbo rocket is a propulsion system that combines concepts from rocket motors and turbojets to enable operation from standstill to high supersonic, low hypersonic flight speeds, with a high specific impulse and high thrust-to-weight ratio. These characteristics make the ATR engine cycle a good candidate for applications such as high-speed point-to-point transportation and as an air-breathing component to space launch systems. This video provides an introduction to the air turbo rocket and compares its characteristics to those of a rocket and turbojet. We'll also look at video footage of recent ATR hot fire testing, some of which is being previewed here. Let's start by reviewing the basics of rocket and turbojet operation to set the stage for a description of the ATR, and then a comparison of the engine to these well-established propulsion systems later in this video. Although there are many possible rocket configurations, for the purpose of this video, we'll focus on the bipropellant pressure-fed rocket due to its similarity to our current ATR development work. The bipropellant pressure-fed rocket consists of a fuel source, such as a liquid hydrocarbon, like kerosene or propane, and an oxidizer source, such as liquid oxygen or nitrous oxide. A pressurization system injects the propellants into a chamber where they mix and burn. The resulting hot, high-pressure combustion products flow out of the nozzle to produce thrust. In a turbojet, fuel enters a combustion chamber where it mixes and burns with air that's been raised to a high pressure by a compressor. The hot, high-pressure combustion products expand over a turbine, which in turn drives the compressor. The remaining pressure head is then expanded through an exhaust nozzle to produce thrust. In an afterburning turbojet, additional fuel is injected into a secondary combustion chamber downstream of the turbine, known as an afterburner. This additional combustion process raises the temperature of the flow before it exits the nozzle and can generate a substantial amount of additional thrust. For example, the afterburner of the Pratt & Whitney J58 used in the SR-71 increased engine thrust by 40%. In flight, an inlet is needed to provide the correct conditions for engine operation. A bell mouth inlet, as shown here, is only used for ground testing. The air turbo rocket combines concepts from the rocket and afterburning turbojet. In the ATR, a component known as a gas generator is used to produce a high-pressure, fuel-rich gas. Here, we're showing a bipropellant gas generator. The gas generator, or GG, can be thought of as a small liquid rocket motor that is operated at fuel-rich conditions, and thus not all of the fuel combusts within the device. The GG of a bipropellant ATR is also conceptually similar to the pre-burner of a fuel-rich stage combustion rocket engine. The GG effluent travels down a gas transfer tube and expands through a turbine, which in turn drives a compressor. The compressor forces ambient air into the main combustion chamber. Here, the fuel-rich turbine drive gas mixes with the compressed air in a secondary combustion process, similar to that of the afterburner in the afterburning turbojet. The resulting combustion products are then expanded through the nozzle to produce thrust. As with a rocket, other propellant configurations are possible for the ATR. For example, the ATR can also use a monopropellant or solid propellant in the gas generator. Regardless of the propellant configuration, the purpose of the ATR gas generator is to produce a gas stream that is hot, at high pressure, and fuel-rich. As mentioned earlier with the turbojet, the bell mouth inlet shown here would only be used for ground testing, and a purpose-designed inlet would normally be used for flight operations. One subtle but very important distinction between the ATR and the afterburning turbojet is that the pressure in the ATR main combustor is much higher than that in the turbojet afterburner. Typically, an ATR combustor operates at about twice the pressure of a turbojet afterburner. This difference in operating pressure is due to the fact that in the ATR, the air from the compressor immediately enters the main combustor, as is highlighted here. In contrast, in the afterburning turbojet, the air from the compressor experiences a significant pressure drop as it expands through the turbojet's turbine prior to entering the afterburner. Because the working fluid in the main combustor of the ATR is at a much higher pressure than that in the turbojet afterburner, even at the same temperature, it has more available energy to generate thrust. As a result, the ATR can produce more thrust than an afterburning turbojet of a similar size. It also has a higher specific thrust, or thrust per unit mass of airflow, and higher thrust per frontal area than the afterburning turbojet. The thrust advantage of the ATR comes at the expense of a higher total propellant flow rate because the source of all shaft power to drive the turbo machinery is derived from onboard propellant supplies. We'll look at the trade-offs between the turbojet, ATR, and rocket in detail momentarily. Before doing that, though, let's look at a prototype air turbo rocket in development by a consortium of firms formed by Bergmans Mechatronics, BSRD, C3 Propulsion, and Streamline Automation in Huntsville, Alabama. Near-term objectives of this work are to demonstrate the basic feasibility of the ATR concept, to serve as a testbed for various ATR hardware and propellant configurations, and to anchor performance prediction models for the engine. Several key components of this gas generator cycle ATR engine are highlighted here. In this view, we can see the gas generator mounted adjacent to the main body of the ATR. Hydrogen and oxygen mix and burn here to produce a high-pressure, high-temperature, fuel-rich turbine drive gas. The gas passes through the gas transfer tube, then enters the turbine and compressor housing, where it spins the turbine. The turbine drives the compressor, which draws in air through the air inlet. The compressed air and unburned hydrogen from the GG mix and burn in the main combustor. The combustion products then expand through the nozzle to produce thrust. Here are two camera views of an initial hot fire test of the engine that was performed in late 2019. Let's watch this test again, this time using the Diadem data processing program to show time histories of engine RPM, normalized thrust, and normalized airflow rate data, along with the camera footage of the test, which has been synchronized to these time histories. As mentioned earlier, the higher thrust of the ATR relative to a similarly sized turbojet is achieved through a higher propellant flow rate. That trade-off is just part of the range of performance characteristics that exist when comparing the rocket, ATR, and turbojet cycles. Let's now take a look at this bigger picture of performance characteristic trade-offs. First, we'll compare the ATR to a rocket. Since the ATR uses ambient air as oxidizer and reaction mass, for the same thrust, it has a lower propellant flow rate and, as a result, a higher specific impulse, or ISP. For the same thrust, the ATR is heavier than a rocket due to the additional turbo machinery and other components required to handle the air. This additional weight results in a lower thrust-to-weight ratio. Comparing the bipropellant ATR to an afterburning turbojet, the higher combustor pressure results in a higher thrust-to-weight ratio and higher specific thrust. However, it has a lower specific impulse due to the higher total propellant flow rate through the gas generator. To provide a sense for the variation in specific impulse across these three propulsion systems, let's compare typical values for hydrocarbon-based versions of each engine. On the low end of the spectrum, hydrocarbon-based rockets have ISP values of around 220 to 300 seconds. On the high end of the spectrum, afterburning turbojets have ISPs of around 1900 to 2200 seconds. The ATR has ISP values in the range of 700 to 1200 seconds. We can do a similar comparison of thrust-to-weight ratios and specific thrust for hydrocarbon-based engines. At the low end of the spectrum, turbojets typically have thrust-to-weight ratios of 2 to 9 and specific thrust of 80 to 120 pounds force per pound mass per second. At the high end of the spectrum, rockets have thrust-to-weight ratios of 60 to 70 and above. Specific thrust is not applicable for rockets since they don't use air. The ATR can have a thrust-to-weight ratio in the 5 to 50 range, and specific thrust in the 80 to 150 pounds force per pound mass per second range. Comparing the three propulsion systems in this way, we can see that the ISP and thrust characteristics of the ATR sit between those of a rocket and turbojet. Although rockets and turbojets are well-established propulsion systems, we believe there is a performance gap between these two technologies, where the ATR can improve existing applications and create new ones. One way to think about possible applications for the ATR is to first look at the existing roles of rockets and turbojets. Rockets, having high thrust-to-weight and low ISP, are best suited to accelerating payloads to very high speeds, such as in orbital launch vehicle or time-sensitive tactical missile applications. An important characteristic of these applications is the large quantity of propellant that is consumed relative to the vehicle and payload mass. This characteristic tends to make rockets best suited for applications where the cost of the propellant and vehicle are negligible relative to the value of the payload or the mission. Turbojets, with their high specific impulse and low thrust-to-weight ratio, are ideal for relatively slow, long-range cruising applications. The high specific impulse of the turbojet, which can also be expressed as low specific fuel consumption, enables the quantity of propellant consumed during a mission to be low relative to the vehicle and payload mass. This relationship enables high reusability of the vehicle, which in turn drives down operating costs. Interpolating between these two extremes, we anticipate that ideal applications for the ATR are those that require a combination of high thrust-to-weight ratio to achieve rapid acceleration from standstill to high supersonic, low hypersonic flight speeds, and high specific impulse to enable high dry mass fractions, which in turn enable aircraft-like operation and reusability. A few example applications for which we think the ATR is well-suited include winged flyback boosters for two-stage-to-orbit space launch systems, high-speed point-to-point transportation, special-purpose drones and target vehicles, consumer applications such as high-performance remote control planes and rockets for use by serious amateur enthusiasts. We plan to continue to improve the performance of our prototype engine and to use test data to validate our engine performance prediction model. We are also planning testing with other propellants, including a solid propellant, direct connect testing to evaluate engine performance at simulated flight conditions, development of a small-scale flight-weight engine, and flight testing. Please contact us if you would like more information about our work.